In this video, we're going to talk about hash tables, but we're actually going to start by talking about associative arrays, which will provide a nice introduction to talking about hash tables and the concept of hashing. So, as we know, a traditional array allows us to store a series of values in a series of elements. And these elements are numbered, they have a position in the array, and we refer to this through an integer value, which is the index. And as we know, we've placed the index in the subscript operator after the array name. Okay, so the associative array still works on this principle of storing values at a numbered index, a numbered position within the array, but rather than referring to this position in the array through an integer value, we can actually substitute that with a more meaningful value, which has an association with the integer index, where the particular value is stored in the array. And an enumerate type is a really good example of this, because remember that the categories for an enumerate type can be assigned corresponding integer values. So here we see that player has the integer value of 0, the type AI, the integer value of 1, and background has the value of 2. So rather than having to write 0, 1, and 2 within the array in main, which is called objects, we can actually refer to the particular category, such as player, AI, or background, each of which having an associated integer value, which can be used to act as the array index. However, this approach of using enumerated types does require us to define the associations between the keys and the values before we run the program. And as well as being reliant on knowing these keys at compile time, we're also not able to add any additional categories and associated values. So in the case where we don't wish to be limited to a set number of defined associations, a more flexible approach would be to create the keys dynamically and then map them onto an index within the array. And this is the concept of hashing. And this is typically achieved by a hash function. And this hash function specifies the code which will translate the key into an integer index. So rather than using the categories of an enumerated type or an integer value for the index of an array, instead, we could use a string as a key and then convert the letters of the string to numbers. Because remember that each letter has a unique ASCII code, meaning that each letter of the string can then be converted to an integer number and can subsequently be used as an array index. As you can see here on the slides, that the lowercase letter a has the integer value of 97. And the letter P, being the first letter of the word player, has the value of 112. But it wouldn't be advisable to rely on the ASCII code of a single letter, because there may be more than one word which starts with that same letter. So therefore, we can create more unique keys by adding together the letters within each word. So here you can see that the string player, we're actually adding to the individual ASCII codes of those letters. So remember that each string acts as an array where the individual characters of that string are stored in separate array elements. So here you'll see key element 0 referring to P, and then key element 1 referring to L, and so on and so on. And then we actually add the ASCII codes of those letters together to create the sum, which in this case is 653. And whilst this helps to prevent duplicate indexes for words which start with the same letter, there are still problems where you have smaller words that have the same letters, but just in a different order. For example, the word AI will have the same index as the word IA. So one approach to solving this issue might be to multiply each of the character's ASCII values by a different number depending upon its position within the word, so that each combination of letters would result in a slightly different index because each of the letters will be multiplied by a different number for each combination. So here, we're using a process which is similar to the conversion between base 2 numbers, which is binary, and base 10, which are decimal numbers. So in that conversion from base 2 to base 10, the digits of binary are multiplied by 2 to the power of a position. So the first digit in binary is 2 to the power of 0, and then the second digit is 2 to the power of 1, and then it's 2 to the power of 2, power of 3, power of 4, and so on and so on. And so we're adopting a similar formula here, but instead we're using 255 as the base value and then multiplying that by the particular position. So if we're in the first position, that's going to be 255 to the power of 0. And then if we're in the second position, that's going to be 255 to the power of 1. Okay, so we use this formula and then we multiply that by the particular ASCII codes of the letters and then sum that all together to create a unique value for each combination. But the disadvantage of using this approach is that it does create very large integer values, which are not desirable for mapping onto indexes of an array. Because if we have an array index of, say, 4 million, that would mean we'd have to create 4 million elements of an array, which is unnecessary if we only want to store a handful of values within our particular array. And so a way to reduce the huge range of keys would be to use the modulus operator, which is the percentage sign on the keyboard. And the modulus operator will return the remainder of a particular division. So if we were to divide the total sum, that large number for the hash key, and then divide that by the total number of elements that we were expecting, we would actually get the remainder of that division, rather than the number of times that the number of elements went into that hash key itself. And so this ensures that the remainder will never exceed the total number of expected elements. The remainder will always range from 0 to the number of elements minus 1. Okay, so it's this approach that we're going to be adopting in the exercises to help reduce that range of hash keys that could be generated. Okay, so speaking of which, let's have a go at getting a hash table up and running. Right, so let's have a go at exercise 1. And in this exercise, we're going to be developing a hash table that stores pointers to game objects. And here we go. We've been given the UML diagram for a GameObject class. So let's get that set up then. Let's add that. I'm going to add a header file. As always, if you want to add both CPP and header, do go ahead. But just to try and reduce the amount of pages that we have, I'm going to create a header. Okay, and let's add the structure for the class. Right, and we have 2 attributes. We've got an integer key, which I'm going to put in the public interface. And then we've got a string name. Okay. I need to include iStream. Okay. Let's try using namespace then. See if that works. Yeah, there we go. Okay, so we need to include iStream and namespace std to get access to the string library from here. Okay, and from there, let's add in the constructor. Key and string name, which they're just going to, these parameters are going to be assigned to the class attributes. So let's fill that in. And let's also do that for the name. Okay, and that's that. Okay, so that's that. Now let's go on and create a class for the hash table. So let's add another file there. Call that hashtable.h. And let's set up the class structure for that. Okay, so we've got a pointer to a pointer here for our data attribute. So our data's going to store, and it's going to be of the GameObject class. So I need to include that, so we can get access to it. And I might as well include IOStream while we're here. And that's also add using namespace, just to be on the safe side. Okay, so now we've got access to the GameObject class. We can create a pointer to a pointer for data, and that's going to act as the hash table. That's going to store the GameObject types in it, and then we've got a size attribute. And I've just noticed these are actually private attributes. So let's move them to the private interface. We've also, I've just seen here as well, we've got a padlock under this function, the hash function here. So I'm also going to put that in the private interface. Let's add that in here. Hash function key. Okay. So from there, I think we can move to the public interface. Let's just create some space here. And let's add the constructor first. Oh, sorry, it's a non-default constructor, so we need to pass in the size. And then we've got a display function. And we've also got an insert function. And that insert function is going to take a GameObject pointer, presumably the item we want to add to the hash table. Yeah, okay. And so let's start filling in these methods then. The constructor should assign the size parameter to the corresponding data member. So yeah, we've got a size class attribute. So let's assign that size from the parameter. Oops. Yeah, no, that is the right place. That is the right place. My constructor. And then I want to instantiate the array, the hash table, size, elements of pointers. Okay, so that's going to be data. That's the hash table, the array that we want to use. And then, because we've got a pointer to a pointer, I'm going to need to assign GameObject pointer there, and then set it up for the size. So it's of that many elements. Okay, I believe that's what that's referring to here. And just for neatness, I put that there. And then what do we do next? We iterate through the array, assigning each element a value of null. Okay, so from here, let's say for less than size. So it's standard for loop, and then within the loop, I want to then assign each element to be null. Okay, and I can use null in uppercase to refer to that value null. Okay, so I think that's that. What's next? The display member function iterates over each element of the array, displaying the index, key, and name, but only if the element is not null. Right, so we're going to need a for loop then to iterate through each element. Oh, tell you what, save time. Let's copy this. Put that there. And then, so if the element is not null, so if data I is not equal to the value of null, it's at that point that we then want to print out the index. So let's say index, and that would be the loop counter I, of course, there. I can reuse that. And then let's say key. Just add a few spaces in here to for formatting. And then I want to say data element I and point to the key. Okay, and then finally the name. Okay, so space name, and then say data element I, and again point to the name there, and then finally in the line. Okay, so we've got a lot going on. Let's put these on separate lines to make it easier to read. Okay, so hopefully that makes it a bit easier to read there. So we're just printing out the appropriate information, the index, the array index, the key, which we're going to be using from the hash function, whatever that returns, and then the name that we assign. Okay, and that's coming up later. All right, so that's that. That's the display method. Next, what we got? We got the insert member function. So, and actually, rather handily, we're provided with the code for this. So I'm going to copy that in here, and that's just going to use the key that's given, and then pass that key to the hash function, which we're also given here. So let's add that in to the, it was the private function, wasn't it? Yeah, add that there. Okay, and that will just return the remainder via using the modulus symbol, and assign that to the hash variable here. And then we're going to assign it at that position which was returned from the hash function, unless that element is currently has been used. Okay, and then if it has, we then just increase the value by 1, and then work out modulus again to see if there's a different space that we can put it. Okay, so we'll see that in action in a bit. So we've done that. We've added the insert. We've added the hash function. And next, we're told to go back to main. So let's do that. And in here, we're given the codes for this. I'm also going to need to include references to the hash table. So let's do that. Oh, actually, let's put it up here. Include hash table. That should already have references to GameObject, but we'll add it in anyway. Okay, so that's that. We're going to create a instance of the hash table, declaring it to be of 17 elements, and then we're going to attempt to add in GameObjects for this data. So the key of 10, and then the name that we're given for these particular objects here. Okay, and so let's run this and see what we see. Excellent. So we're told to compare it against the output here, and as you can see, we're matching the indexes nicely, and also the keys, which is good, and also the names. Interesting thing to note here is that you notice that we attempted to add in a key of 30, which exceeds the total number of array elements, which was 17. So we then take the remainder, that is 30 minus 17, making 13 here for this index. So that's good. That tells us that our hash function's working correctly. Okay, so next, here's where we get to collisions. Now's probably a good time to pause, because in the next section we're going to talk a bit more about collisions. So yeah, let's pause here and let's jump back into the slides and talk about collisions. So the use of the modulus operator in the hash function does drastically reduce the potential range of hash keys to the size of the array, and it also improves the likelihood of generating unique hash keys for each item that is being added to the table. However, this doesn't completely eliminate the duplication of hash keys, and a term which we're going to be using is collisions from now on. Therefore, it's necessary to think about ways to resolve these collisions when they occur. And techniques for resolving collisions tend to fall into two categories. The first is open hashing, where colliding items are stored outside of the table. And the most common of these is where they're stored in a linked list. And then secondly, there is closed hashing, where colliding items are stored inside the hash table, but at an alternative slot in the array. And so in this video, we're going to look at two techniques, one from each category of open hashing and closed hashing. The first technique we're going to have a look at is open addressing, which you may think that because of the name being open addressing, it would actually belong in the open hashing category, but actually it belongs in the closed hashing category, because in open addressing, we actually create an algorithm to find an alternative location within the array. And then the second technique, which is a very popular one, and that's the technique of chaining, where we would create a linked list at the element in the array where there are duplicate hash keys, and then we store all of those duplicate hash keys as nodes in a linked list. And then we would have to go to that item in the array and then iterate through the linked list nodes in order to find the node with the particular value that matches what we're looking for. Okay, so we're going to start by discussing open addressing. And there are three solutions to resolving collisions using open addressing. The first of which is linear probing, which will start probing the consecutive array elements from the duplicated hash key to see whether there's an available space to insert this new item. However, repeated use of this technique can lead to what's known as primary clustering, where the items end up being stored consecutively in the array rather than the position which was supposed to be associated with the ASCII codes of the string itself. And as more and more items are being stored in hash keys unrelated to the word itself, that will degrade the performance of looking up items in the hash table. So we could use, secondly, quadratic probing, which similar to quadratic time, the big O measurement, which is n squared. Quadratic probing, therefore, is where we square the probe each time, meaning that we will probe at ever increasing intervals. So the first interval will be 1, because 1 squared is 1, and then when we probe again, 2 squared will be 4, and then 3 squared will be 9, and then 4 squared will be 16, and so on and so on. Meaning that we can then start to spread out the duplicated hash keys in different locations within the array, not consecutively, as we did in linear probing. And whilst this is an improvement upon the problem of primary clustering from linear probing, quadratic probing actually creates the problem of secondary clustering, because the algorithm being applied, the geometric increase, is predictable. So we actually create clusters of keys, but just with more spaces in between them. So therefore, to avoid both primary and secondary clustering, a third technique was created, called double hashing, which is where keys are hashed a second time using a completely different hash function, where the value returned from this function is a step size. But for this to work successfully, it's important that the size of the hash table is a prime number. So consider the illustration on the left-hand side, where the size of the array is 15, which isn't a prime number, and if the step size was, say, 5, then once the multiples of 5, 0, 5, 10, and 15 are full, the algorithm gets stuck in an infinite loop and has no place to insert the new item. But if the size of the array was 13, which is a prime number, then the cycles will end up starting on a different number each time, because they'll eventually overlap. Once we get to 10, we then move 5 ahead, which puts us not at 15, but back to 2, which is different from the starting place of 0, creating a different set of positions in the array to probe, and to hopefully find a free one to then put the new item in. Okay, so those were 3 separate solutions for open addressing. Now let's move on and have a look at separate chaining, which is an example of open hashing as opposed to closed hashing. Okay, and in separate chaining, we create a linked list at the positions in the array where there are duplicate hash keys. And the advantage of employing this methodology is that we can maintain the fast lookup, which is constant time, O of 1, because we're storing the hash keys in the positions that they were intended to be stored at. There's a direct relationship between the string word and the position in the table. However, it does then take linear time in order to iterate through the nodes in the linked list. But providing we don't have too many nodes in the linked list, this shouldn't sacrifice on the performance too much. But of course, this will become a problem if we have lots of nodes in the linked list. So in summary, we've seen that hashing provides a way of translating keys, which are strings, to integers, which can be used as indexes of an array. And this then allows us to use strings as indexes of the array, meaning that we can look up items in potentially constant time, providing that we've coded the hash function in an efficient way. But this is great because if, say, we wanted to find out the phone number of a contact, we could use the contact's name as the index to get instant access to the phone number, rather than having to, say, employ binary search, which is at best logarithmic time, in order to split the data structure several times in order to find the contact details. So therefore, constant access is a huge advantage to using a hash table. However, there are problems with collisions, or in other words, duplicate hash keys, as we've seen in this video. And it's important, therefore, to think through the most appropriate way to resolve these collisions, and whether you'll use a technique from the open hashing category or the closed hashing category. Okay, so that's enough about hashing for now. Let's carry on with the exercises then, and continue to implement our hash table. Okay, so now that we've had a look at collisions, let's continue from where we left off in the previous exercise. Right at the end of the exercise, we were asked to insert another GameObject that will cause a collision with the AI object. And then we're asked a follow-up question of why it was placed at element 0. Okay, so let's explore this a little bit then. So let's say I wanted to insert another object at the same position in the hash table as the AI object. If I was to call this AI dupe, short for duplicate, and run this, let's see what happens. Aha, okay, so we attempted to store AI dupe at position 16, which has the same position of AI, okay, but notice this AI dupe was actually stored at position 0, which is what the question asks. Why is that? Okay, so let's go back to the hash table and have a look at the insert method. Okay, so have a think about this. Why would it be stored at position 0? Okay, could it be to do with this part here? Okay, so with the key, we're attempting to store it at position 16, but when there is something at that position, which is this bit, we actually increase the value of the key, don't we? So 16 would become 17. And think, how many elements in this hash table do we have? How many did we set it up to have? 17. Okay, so we increase 16 to 17, and therefore if we attempt to divide 17 by 17, that's going to go perfectly, isn't it? Because remember, we take the modulus of that, that key to get the index. Okay, so because 17 goes perfectly into 17, we have the remainder of 0, meaning that that is going to be our hash key. Okay, hence why we're going to store that at position 0. Okay, as a reminder, there we go. Okay, so that's the reason why it's stored at position 0. Okay, and let's, before we let you carry on with the rest of the exercises, let's quickly get you started again with exercise 2. So for exercise 2, we are instructed to add a find method. Okay, so I'll get you started on this one then. So we're given the signature, which returns a GameObject. So the function is called find, and then we're going to search for an integer, and that's going to be the key that we're going to look for in the hash table. Okay, and then for exercise 2, again, we're given the pseudocode, so we just got to convert it. So let's do that step by step. The first line is to define hash as type int. So that sounds like a temporary integer variable. Okay, and then we want to assign it the hash for the key. Okay, so let's translate that. That would mean calling the hash function to generate the hash for the key that we are passing into the find method. Okay, so we're just going to pass that straight to the hash function there. Okay, so that's that bit. And then we're going to loop through the elements of this hash table. So while data hash is not equal to null, whilst the value at that position is not null, we want to say, well, if the particular value we're looking at currently, if the key of that object matches the key we're looking for, then we want to return that value, or that object, I should say, rather specifically. Okay. So from there, end if, and then want to increment hash, and then we set hash to be hash mod size. Okay, so as we have done previously, we would say hash equals hash percentage sign size. Okay, end loop, and then return null if none of the above matches. Oops. Okay, so that's that. That's the pseudocode translated. And then we're now instructed to try and locate and display the tank object. So let's go back to main. And tank has the key of 30. So let's see if that can find it. Okay, because remember that should be stored at position 13. Okay, so let's see if our find function can also find that index. Right, so let's set up a pointer to GameObject, and let's call it item to find. Okay, because remember our find function is going to return a GameObject. Okay, so from there I can call the find function through table, passing it the key of 30. And then I want to assign the returned game object to my my object that I've set up here. Okay, and then I can just have a simple if statement to say, well, if the item to find is not equal to null, i.e. if there is something there, then we can say item found. Or we could be more specific and output the particular details of that item if we want to. But just to keep things simple for now, let's just output whether it's found or not. Okay, so let's put this to the test then. Let's see whether it can translate and find that key. Aha, and it does. Okay, so it's successfully translated 30, because remember there is no index 30, into the index of 13, okay, via the hash function. And it's obviously found the tank, which is good news. Okay, let's just again test this. Let's say if we type in a number that isn't there, either a key or an index. Let's try 9, just to check this doesn't find it. And yes, doesn't find it either. Okay, so that's good. That tells us that our find function is working successfully. Okay, so from there then, I'll release you to have a go at the next exercises then, which is to implement a delete method, and then have a go at creating a hash table that works with strings, where you can use the string as the index when you're using your hash table. That'd be a really good exercise to do. Okay, so give them a go and see how you get on.